Now, in the packet that you received in class, and also if you're watching online, these are the basic steps to balancing a redox reaction using the oxidation number method. We will be discussing the secondary method using the half-life equation in the next video. So the first step is to assign oxidation numbers to all atoms in the equation. The second step, you will then identify the atoms that are oxidized and the atoms that are reduced, the skills that were taught in the previous video. Then you'll have to determine the change in oxidation number for the atoms that are oxidized and for the atoms that are reduced. You then make the change in oxidation numbers equal in magnitude by adjusting the coefficients in the equation. And if necessary, you use the conventional method to balance the remainder of the equation, meaning you add the necessary coefficients to finish balancing. So let's look at two examples. First, we have this lovely equation. Now, if we follow our rules that you hopefully just paused the video and wrote down, if not, go back. Our first step one is to assign oxidation numbers to all the atoms in the equation. So, we start. We know our oxygen. Each oxygen is a -2. -2 times 3 is -6. If I need to have a -2 overall, that means the selenium has to be a +4. So that I have a -2 overall charge. This is really times 3, -6. Now, this iodine is listed as a singular ion, so this is indeed just representing a -1 charge. Here, selenium is neutral. It's in its atomic form, so it would have a charge oxidation number of 0. And I2 would also have an oxidation number of 0. So our second step, according to our steps, is to identify the atoms that are oxidized and the atoms that are reduced. So if we notice, our selenium went from being a +4 to a 0. And to do that, to go from being +4, meaning I have more protons than electrons, the selenium had to gain 4 electrons to get back to 0. Think number line. So realize that 0 is same number protons as electrons. So when I have a charge of +1, that means I've lost an electron. Lost 2 electrons, lost 3 electrons. Got them back to be 0. But when I go to the negative side, -1, -2, -3, that means I've gained. So I've gained electrons, lost electrons. Perfectly neutral here. So if I go from a +4 to 0, I'm going towards the gain side. That means that I had to gain electrons. So that means that my SE, since reduction is gain, rig, selenium is reduced. So I'll look at my iodine. Okay. I2 goes from -1 to 0. Well, to go from -1 to 0, I'm going towards the lost side, meaning I had to lose an electron. So it lost specifically 1 electron. So then I know for sure that iodine was oxidized. Now you're probably thinking, well, wait a minute. There's an oxygen on the left side, but there's no oxygen on the right side. Did she write it down right? I did. But notice, it tells me we're in the acid form. We'll deal with that in a moment. Now, following our steps, step 3 asks us to determine the change in oxidation number for the atoms that are oxidized and for the atoms that are reduced. So we already decided that selenium, so the change for selenium was a 4, and the change for iodine was 1. You're basically looking at the overall, just the general change, not lost or gained, but just general change. So this isn't so difficult. We're just getting the net change. Now step 4 is where it gets a little hinky. So where it says in step 4 to make the change in oxidation numbers equal in magnitude by adjusting the coefficients. So the easiest way to do that is to essentially do a swap. So if I have my SeO3 -2 plus the I negative, Se plus I2, well, I know that if selenium, each selenium needs 4 electrons, but iodine is my electron donor, then I need to put the 4 with the I so that I'll get 4 electrons donated, and the 1 with the selenium. Okay? So now I have enough electrons being donated so that everyone's happy, but the problem is step 5. I have to use conventional method to balance. But I have a whole element on the left that's not on the right. That's where this lovely acid comes in. Please remember that when you're working with something that's in an acid, that we are allowed to add water, H2O, to fix an oxygen problem. And then generally when you add water, you add hydrogen as well, so then you have a hydrogen problem, and you can add hydrogen ions to fix that. We can add hydrogen protons because this is in an acidic solution, and by definitions, acidic solutions have an abundance of hydrogen ions. So back to our problem. So since I have 3 O's over here, that means I'm going to need 3 H2O's over here to give me 3 O's to fix my O problem. But when I do that, it adds 6 hydrogen. So now I have hydrogen on the right, but no hydrogen on the left. But I can fix that by adding my 6 hydrogen, my 6H plus. So we have 6 hydrogen ions, 6 hydrogen ions. 3 oxygens, 3 oxygens. 1 selenium, 1 selenium. We had 4 iodine. Whoops! We don't have enough iodine over here. So we add our coefficient in the traditional fashion. And now we have our 4 iodine on the right. And you have a lovely balanced equation. We're representing that these 4 iodine are donating from here to here. They donate, so they lose 4 electrons. And those 4 electrons are picked up by the selenium because the selenium was going from +4 to 0. So it needed those 4 electrons. So let's try another one because I know this is rather confusing.